Hello, hopefully you can hear me. I should say bonjour as well to our French colleagues. So, as Gregor says, I work at the Royal Observatory of Edinburgh. I work slightly with the technology group there as well. So tonight I'm going to talk about stellar evolution, and in particular about the hertzsprung-russell diagram, which is becoming part of the curriculum. So that diagram is the diagram which you see on the background of my first slide here. It's not the most exciting looking thing in the world, but there's an awful lot of very interesting and very important physics in there. So my plan tonight is to try and sort of go through stellar evolution and build up that figure. So break it down to what it's telling us and build it back up again. So as I go along, I'm going to keep coming back to this friend of ours, which is I hope you recognise, is the Orion Nebula, Orion constellation, which is the famous constellation you see on the night sky. Orion here with his 3 stars making up the belt. Orion is a brilliant example of stellar evolution. There's lots of different types of stars in there, and I'm going to draw out a few of those as I go along. So the structure tonight is roughly like this. I will begin by talking about how stars are born and the early stages of their life. I'm then going to talk about different types of stars and particularly talking about their colour and their temperature, which is kind of what the hertzsprung-russell diagram is. I'm going to start calling it a HR diagram as well. Someone's saying they've lost. Okay. So it's HR diagram rather than hertzsprung-russell diagram because it's a lot easier to say. So I'll say HR diagram. I'm going to talk to you a little bit about massive stars because that is my area of research, and I'm afraid to say you're my captive audience, so you're stuck with a little bit of what I do. And then from that, I will go on to talk about the eventual fate of some of these stars and a little bit about how we get their ages from that diagram. So star formation happens nicely in some beautiful patches of the night sky. These are the famous pillars of creation, which was a wonderful picture taken by Hubble, which has become extremely well known. The idea here is that within those clouds of gas and dust, there are young stars forming. We can sort of zoom in on one of those patches and see a sort of this is effectively one star, one young star, which is within the middle of that cloud. The material is collapsing under gravity, leading to the central regions heating up heating up and also getting under very high pressure, and that is essential because once we reach a certain point where it's hot enough and the pressure is high enough, then atoms are able to fuse together and we have a star. We can look in more detail at the inside of this region using infrared light. So this image you're seeing now is a picture taken with visible light with Hubble, but they've also taken infrared images. So this is the same patch imaged twice. So I'm going to flip between them and you can see the difference. And the really exciting thing is that right in the heart of that region is the young star, is our newly formed star. And bizarrely and intriguingly, not well understood, you can sort of make out whitish stripes coming out from either side of the star in the center of that region. They seem to be jets coming out of the side of the star. So the star is spinning. It's in a disk of material. I'll come to that. And you get these jets coming out of the side, which is a really interesting thing because it's not brilliantly understood as to why or how those jets are formed. But that's a very active area of research. The trouble is, it's quite hard to study the young star because it's so deeply embedded in all that material, all this gas and dust, effectively obscures our view. We need the infrared and to study these things. So if we were to have an amazing telescope, we might get a view like this. This is not a real picture. This is a simulated image of that young star and with its disk, a dusty disk of material around it. This is actually the star has formed, so it's probably a little bit later than the process you see here. It says probably a few million years later. The star itself has formed, and the disk material is there. And actually, within this disk, if you look closely, you can probably see there are a few young planets forming. So this is how we think star formation and then planet formation happens. And we can actually go, and the nearest place you can go and look for this yourselves is to go and look at Orion and look at Orion's sword. So you have Orion's belt, which is the three bright stars in the middle, and then hanging down from Orion's belt is his sword, or as I've heard people in Scotland trying to claim it's called a sporran, but I'm less sure about that. I'm going to call it a sword. The sword is actually a nebula. So in this sort of picture, which is a long exposure, so it's a bit more sensitive than your eyes would see, you can hopefully see that the sword region is sort of a slight. Doesn't look like a star. It's glowing a little bit more, and it's actually a cloud of gas and dust. It's one of the only things you can see on the night sky which isn't just a star, isn't just a point of light. It's an interesting thing to think about. When you look at most things on the sky, it's either a collection of stars like the Milky Way, or it is just it's just a single star, whereas this is actually a cloud of material. So if we zoom in on that using a fairly powerful telescope, it has to be said, you see something like this, and you can see all this glowing material, a little bit like the pillars of creation, and in the middle there are some young stars formed. But interestingly, in Orion, we actually see, so this is zooming right in, and these little blown up regions are pictures from Hubble Space Telescope again, where you can see the early stages of the star formation process. The one at the top, sort of of the insets, the top inset is a really nice example. The disk there is edge on to us. So there's a cloud of sort of glowing material, and then you have this disk of material around the star, which is sort of being obscured, so we see its shadow. Now this actually historically been a really good example of star formation and an area we've studied a lot. But we have new telescopes, and so just earlier this year, end of last year, there was a release of data from one of the new telescopes, and so this is a real image now of a star formation region, or of a young star with a disk material around it. This was taken with a new telescope in Chile, and it's tremendously exciting because actually, if you think back to that picture I showed earlier on of the disk of material and the young planets, this looks reassuringly like what we thought it would look like. So you've got your young star in the middle, you have a disk of material, and then we think that these stripes around the star, the sort of dark bands, are where planets are forming. We think planets form, I know we're meant to be talking about planet formation, but because it's interesting. We think planets form, I think a little bit like if you think of taking a snowball and rolling it around in the snow, and the snowball gets bigger and bigger as you roll it. It's a little bit like that. Just see glowing material. So generally glowing material. Generally glowing material. It's actually it's relatively faint, which is why we quite often have to have long exposures to see it. There is reflection as well, but generally glowing. Okay, so after all that time, we've had our disky material and planet formation, which we talk about more if anyone wants to ask questions later on. We get a nice stable star. So this is an image of our own sun, and one of the key things to think about when you look at a star like this is that it's a brilliantly stable system. I know actually when you look closely at the sun, the surface is very active, but in reality it's remarkable that this object sits in a relatively similar state for a few billion years. It's a very well balanced system. So within a star you have the gravitational pressure, which is trying to make, just naturally the gravitational pressure is causing the outer layers to fall inwards. But then in the core of the star there's the nuclear fusion occurring, which is creating a lot of radiation, which is pushing outwards. And the star is the balance between those two forces. So between the gravitational attraction and the pushed outward force from the fusion and the radiation created with the fusion. And the beautiful thing is that actually they regulate each other. If the star expands slightly, the fusion rate at the core drops. and therefore the outward pressure drops, and therefore the star will slightly contract. And likewise, if it were to contract too much, then the core would heat up, it would have greater radiation in the center, and it would expand. So it regulates itself, which is a pretty key idea. It's pretty important. It's part of the reason why a star is so stable and why they can last so long, which is pretty important for all of us. Within this image, there's a couple of things I want to point out, one of which I'm sure you're well aware of, and that's this, just to say that next Friday, no, not tomorrow, but on the 20th, there is an extremely impressive eclipse happening as the moon passes in front of the sun. It's not at all relevant to stellar evolution, but just in case you weren't aware of it, it's 95% or something like that across the lot of Scotland. The further north you are, the better it is. And if you happen to be in the Faroe Islands, it's going to be 100%, which is pretty exciting. It's one of the best eclipses we're going to get in Scotland for quite a long time. So look out for that. But be careful; it's still plenty bright enough to blind you. But it's worth trying to look at if you get the right equipment, I should add. The other thing to point out, which is completely irrelevant, but just because I always like pointing this out, this picture was taken by a fantastic amateur astronomer called Thierry Legault. And if you look closely at that thing, which looks like a sunspot, you see it's actually the International Space Station with the shuttle docking at the International Space Station. This chap's an amazing photographer. I say completely not at all relevant to stellar evolution, but I can't resist pointing out this man's photographs. Okay, so moving back on, what's happening in the core of the star? This is the sort of the key reaction chain. There are multiple different ways in which atoms fuse within the sun. But this is perhaps the dominant one. Well, it is the dominant one. So this is where we take hydrogen atoms, so the most simple type of atoms, and they are fused together and built up to form to form a helium atom. So the first stage is that you take two hydrogen atoms, they're bonded together to form a deuterium atom, and then also a positron as well. And some neutrinos. Lots of neutrinos always being generated in the sun. The next stage after that is to fuse one of the deuterium atoms with a hydrogen atom, and you get an isotope of helium. And then finally, you take two of those helium isotopes, join them together, and you end up with a helium atom. And all the way along that process, you are releasing energy and potentially releasing something gone funny with the slide there. I don't know if that's happened to everybody, but you are releasing energy, and if you release a positron as well, that will interact with an electron and annihilate, and you'll get more energy. So that's kind of key. You're going from the hydrogen atoms to helium atoms, which is becoming more stable, and so you're converting the mass of those hydrogens, or there's a loss of mass as you go from the hydrogen to the helium, and that is, of course, E equals mc squared, and therefore energy, which is, as I say, pretty fundamental to us. The other thing to point out here is that in this process, the first step is very, very slow. The first step, where you take the two hydrogen atoms and create the helium, the deuterium, is a very slow reaction. The chances are that two protons, two hydrogen atoms, will actually just fall back into being two hydrogen atoms again. And because this is slow, then it actually means that the star lasts a long time. If that reaction was quick, the star would burn through all its fuel. If it was a very quick reaction, the star would burn through its fuel in a few years, and it would disappear. So the fact that that reaction is slow is very important. There's a comment saying, is that the only possible fusion? No, so there are others. And there are others as the star gets larger and hotter, and you start obviously burning, fusing helium atoms as well to form other things. I'll come to that, but there are other ways to go from hydrogen to helium. But this, I think, accounts for about 85% of that process. So for every 100 helium atoms, you end up with 85 of them will have come through this process. What causes it to actually go slow? I think it's the probability I'm not quite sure, but I think it's the probability of what will happen when the two hydrogen atoms have fused. They are more likely to return to hydrogen atoms, I believe, but I'm not 100% sure on that. One other slightly interesting thing to note about the hydrogen, the fusing process, is just to say that if you take two positively charged protons and you try and combine them, they obviously naturally are going to repel a great deal. You have to have very high temperatures or very high pressure, so they're moving very quickly to actually fuse. But remarkably, it's still not hot enough and dense enough for this to always happen in the sun, and actually you have to rely on some quantum tunneling to actually get the two to interact. So this is when we're talking about quantum effects and things going through walls, etc., which always sounds fantastical and ridiculous. This is actually happening in the sun continually in order for hydrogen atoms to ever be able to fuse in a star the size of our sun. Right, so moving on, we will. I hope I'm sort of vaguely answering the questions. It's quite tricky to keep track of the questions as they're coming in. So we'll move on to look at a few things about different types of stars. So as astronomers, we basically all we can do is take pictures of the stars. Well, the simplest thing we can do is take a picture of the stars. So this is a very simple picture with a telescope was taken in Edinburgh of a patch of stars, and I've slightly falsely coloured it red because this picture was taken with a red filter. And what we do, what particularly we've historically done, is we take pictures using filters to measure the brightness of the stars at different colours. So we take a red picture, we take a green picture, we take a blue picture, and then we measure the brightness in each of those different frames. This is as simple as we have a detector in the telescope, and we put a red piece of glass in front of the detector, we put a blue piece of glass, we put a green piece. It's that simple an idea. And you can actually get into a discussion here about colour images, etc. When we have things like Hubble Space Telescope pictures, everyone always says, are the colours real? And the answer is sort of often not quite. We've often taken three pictures, we've taken a red, blue, green picture, whatever it might be, and then we add them together, and sometimes we might make a bit more of the red one than we do the blue one, so it's a little bit of tweaking. But it's an interesting thing to think of, that we can't actually take a real colour picture. Even your phone camera doesn't take a real colour picture. It has a set of filters as well. It's a bit more sophisticated than this, but it's still just filters. So we take our three-different pictures and we use those to then assess the brightness of the stars at different colours. So this is the hertzsprung-russell diagram. This is the key diagram. And if we sort of strip it down to its essentials, you have on the y-axis effectively the brightness. Okay, so if you actually look at it, it's a magnitude scale which appears to be going the wrong direction. Unfortunately, we have a bizarre magnitude scale in astronomy, which is the fault of the ancient Greeks, apparently, that they started numbering things in an inconvenient way, where 0 was the brightest stars and 6 were the faintest they could see. We still use some extrapolation of that system, unfortunately, but which means that actually a 10th magnitude object is a lot fainter or a lot less bright than a 0th magnitude object. But forgetting about the actual numbers, the key is that on the left here of the diagram we have brightness. Along the x-axis we're measuring colour, and in fact what we do is we measure redness. And when I say that, what I mean is that we actually measure the star when taking a red picture and a blue picture, roughly, and we compare the two. And so we give a figure of merit based on how much redness there is along this axis, which is a slightly odd idea, but it works, and we'll come back to it in a moment. Right, so if we get rid of all the data for now, we can just start off by plotting our own sun on there. So here we have our sun, which is pretty much in the middle of the graph because it's pretty much middle of the road kind of star. In fact, I've deliberately coloured it slightly green because our sun is, strictly speaking, green, but we'll come to that as well. So obviously if you look out on the sky, you see a whole host of different stars of different colors, different shapes and sizes, well not shapes actually, different sizes. So if we try and look at the spectral properties of those stars, we see a pretty important idea. So all the stars we look at are black bodies, and as you will know, I'm sure, a black body has a very particular spectral profile. So if we look at the amount of flux or amount of radiation given out at any particular wavelength, you get a profile which looks roughly like this, which is the famous Planck function. And of course, the key thing about this is that it doesn't matter what the object is. Any object at the same temperature will have the same associated, will give out the same associated radiation. Whether it's a piece of iron in a furnace on the Earth, whether it's a star, whether it's you or me, we're all on that same scale. What happens is the peak shifts. So if you have a cooler object, the profile has a slightly different shape, and the peak position moves. So for hotter objects, the peak goes towards the blue. So things start off, well, if you think of us sitting here at 20 degrees, or I think it might be more than 20 degrees in this room, we have a peak wavelength which is of the order of a few microns. If we got hotter, the peak would shift across to the left on that graph. The shape would change, and you would see the same profile. If you heated up us up enough, okay, we would melt, but we would have, if we didn't melt, we'd have exactly the same spectral profile as the sun. So one of the other key things, which I think is part of the curriculum as well, is Wien's law, which relates the peak brightness, the wavelength of the peak emission to the temperature of the object. So it's an inverse relationship. So as I say, the hotter the object, the bluer the peak. So it's a fairly key idea. And the other important thing here is that the object, these lines on the graph don't cross. So that means that it's sort of they're uniquely identifiable. If you measure a few points on this graph, if you measure a few brightnesses at different wavelengths, you can effectively fit this line just for a few points because there's no way for the data to overlap. So what we want to try and do is find that underlying shape. So just of interest, here's the emission for the sun, so this shows the sunlight at the top of the atmosphere, and it also shows the absorption. But ignore the absorption a minute. The only thing I want to point out is just to say that you can see the peak emission from the sun is in the visible part of the spectrum, which is probably no coincidence that our eyes have evolved to see the light, which is the majority of light which is given out from the sun, which is kind of an interesting question. You can talk about different stars, because some stars are peaked in the ultraviolet, some in the infrared. Well, perhaps we'd have different types of eyes if we lived on those planets. There are issues of absorption in the atmosphere as well, but we'll move on. So just coming back to that graph, if you imagine what we do is we use our red filter to measure the brightness in that sort of shade in that band there, and equally we have a blue band. It's simplification, but basically we measure the brightness in those two wavelength windows using the filters. And then we can compare the brightness. So you can imagine that if the object is that red line, obviously its red value, its red brightness is higher than its blue brightness, and vice versa for the object which is drawn in blue here. So by comparing these two frames, we can estimate the temperature. So if we go back to our hertzsprung-russell diagram, we can start populating it with those different objects, and you'll see that we actually, because at different values, so I just go back actually, the flux is always brighter for the hotter objects. It means that our graph starts to look like this, and if we did it for a whole, well, sorry, I should say, so that's the color, but it's also the temperature, effectively. We're effectively plotting temperature along the bottom here. So you see the HR diagram with colors, you also see it with temperatures. Am I rubbing that out as I move the mouse? Sorry. So we also So if you plot loads of stars onto this graph, you get this really important and simple pattern, which is the main sequence. So this pattern, if you go and plot, you collect a random group of stars and analyze them, put them up on the HR diagram, you would get this pattern. And this is the region where the star is sitting burning hydrogen in its core, or fusing hydrogen. I shouldn't say burning, but fusing hydrogen. And it's the main part of the lifetime of the star. So say for our sun, it's sitting on that main sequence, and it's been there for about 5 billion years. It will be there for another 5 billion years. Depending on the object, the time it sits on the main sequence varies. So a bigger star will spend less time on the main sequence. But that's its core hydrogen fusing time. When it starts to use up its hydrogen in its core, it will start doing different things. I'll say that in a minute. So I'm very quickly just going to show you a couple of things about massive stars, which are really objects which would lie right up here at the top left-hand corner of this graph. Very hot, generally actually peaked in ultraviolet. So I study a group of stars in the Magellan clouds, which if you're lucky enough to go down to the southern hemisphere and get into a dark place, you'll probably have seen that the night sky actually is much more impressive than our night sky. They happen to look towards the center of our own galaxy, whereas we are confined to look slightly out away from the center of our galaxy, just by sheer chance. But they can see the two small objects, so I've highlighted one of them here, which is the Large Magellan Cloud, and just below it, to the left, you can see the Small Magellan Cloud, which are dwarf galaxies which are getting swallowed by our own galaxy. So if we zoom in on the Large Magellan Cloud, this is the galaxy here. It's about, the mass is about 1/100th, maybe slightly less the size of our own galaxy. The region I'm interested in is that knot of stars over to the left, about 2/3 of the way up. And that's a region of really, really active star formation. And it's called the Tarantula Nebula. So if we zoom in on it again, so you can hopefully see it's that bit over on the left there, you zoom in. It's called the tarantula because it's got these spindly bits of material coming out. Doesn't really look like a tarantula, but anyway, never mind. So just to, so you go right into the core of that region, there are a whole host of, as you can see here, very blue stars, very hot stars, things which are maybe 10 to 100 times the size of our sun. In fact, we don't know what the upper limit is for a star. There are some people who claim they found objects which are about 250 times the mass of our sun in this central region, but that's a bit disputed because we're not quite sure. Stars start to fall to pieces when they get really, really big, so we don't quite know how big the biggest stars are. This is a sort of image to give you an idea of just the sort of size we're talking about. The yellow star there is our own sun. The light blue object is Rigel, which is the left foot of Orion, or the right foot as you look at him, but it's his left foot. And then the big blue thing you can see behind is one of these massive stars. So these are very large. So this is for the idea of the 250 times the size of our sun. So just to give you a sense of scale of this, here's Orion again. Here's our friend Orion. You can hopefully make him out. You might have to squint a little bit to make out the brighter stars, which is a useful technique if you're outside and there's too many stars. Squint a bit and you can see the brighter ones. Help you find the constellations. So Orion's in the middle. You can see the Orion Nebula there. If you took the Tarantula Nebula, which is a long way away from the Earth, dragged it to the same distance as the Orion Nebula, which I showed you pictures of earlier on, it would look a bit more like this, which would be nice. It would be quite an impressive thing to go out and look at on the night sky. It's also possible that there might be issues about too much UV radiation coming from those stars, and we might all have terrible cancers, but that's another issue. But it looks very nice on the sky. So unfortunately, this is what I actually look at every day, so I study the spectra of the object. So I'm talking primarily today about filters and measuring the brightness and the colors, but invariably a lot of astronomy uses spectra to look at the objects. This is a system where we have we look at the data from 100 stars all at once, and so this is the actual sort of raw data you get off the telescope, which is lots of spectra. You can see there's a bright emission line which is common to all the spectra. Sort of well, there's 3 bright emission lines over on the left-hand side there. which appear in the same point in the spectra of each one. We extract the data, and we get something which looks a bit like this, which doesn't look very exciting in comparison to those nice pictures, but has lots of science. Because you see stars do strange things. So that's data for the same star, and you've seen that it's spectral lines. So the absorption lines you see within the star can get split if the star is actually two stars, which we found here. Often when you look at a star, you're not looking at one star, you're looking at two stars which are close together going around each other. If their shifts are at the right position in their, if you see at the right position in their orbits, you see a shift in the spectra. And so that's what happened here. And that's what we're doing. We're looking at the, we use the spectral lines to measure the velocities of the stars. And we learn a lot about that. So one of the other things we're doing is looking at things like how fast the stars are moving relative to us. And we see that most of them are in a nice group, but you get some weird runaways. So on that graph, you've got speed going along the x-axis and the number of stars on the y. And you can see there's a few objects which seem to be rushing away from us at high speed. And so we think, if we look at the cluster as a whole, those red objects are ones which seem to be rushing away. And we think what's happened is they were in a binary system. One of the stars might have exploded, and the other one's been sort of sent off into the distance, and they're sort of fleeing the nebula. So we've got time with Hubble to go and study it and try and see where they're moving. Anyway, that's a brief aside about massive stars and the sort of things I'm doing. So coming back to task, we'll look at the sort of the fate after things leave the main sequence. So very loosely, we've sort of considered the stellar nebula. We looked at the idea there's average stars, and then there are also these massive stars. And the reason I've separated them is because they will follow slightly different evolutionary paths. So, as I say, at the moment they're all sitting here happily on the main sequence. And what's happening is, as I say, in the core, the hydrogen is burning. So I keep going, is fusing. But then, once the hydrogen levels drop within the core, it can effectively slow down, if not even stop, the fusion of hydrogen with the core. We often talk about once all the hydrogen is used up within the core. It's a slightly dangerous thing to say. It's not quite the case. There's still plenty of hydrogen in the star. It's just there's just less of it in the core, and so the fusion process effectively will cease in the central regions. And what happens then is that the star the central regions start to contract. And actually this can then lead to hydrogen fusing in a region surrounding the core where the hydrogen levels are higher. So you've lost hydrogen from the center, well, you've used up your hydrogen somewhat in the center, and then the hydrogen around the outside begins to fuse. Now, because this is nearer the edge of the star, effectively, it's sort of it's further from the central regions. The outward pressure is therefore able to cause the star to expand. That beautiful balance which we were talking about earlier on has been slightly disrupted, and so the star will swell up and gets considerably bigger. And this is when we start talking about it moving into giant phases, so red giant phases or red supergiant phases, depending on the size of the star. But the principle here is to think that there's hydrogen burning in a shell around the nucleus of the star, and then this swollen, reddened envelope. And eventually what can happen is that actually because there's the fusion around the shell as well, it does lead to a sufficient heating in the core that the helium can start to fuse and can start to generate heavier elements. So things like carbon, oxygen, right up to iron, depending on the size of the star, but things will keep fusing. As I say, one of the key things here is that your star has expanded, and this actually means that the outer layers of the star cool. Because effectively, in some ways, you've got roughly the same sort of amount of energy spread over a larger volume. The outer layers, and also they're further from the central fusing regions, the outer layers will cool significantly. And this is a significant process. You're talking about a massive increase in size, as I'm sure you're well aware. But the outer layers of our own sun, at some point, will almost definitely swallow up Mercury and Venus, and quite probably swallow us as well in about 5 billion years once we've left the main sequence. Say we've got red giants or red supergiants depending on the progenitor, so where the star started. And just to give you an example of one of these, again, let me turn to our nice faithful friend. As I mentioned earlier on, this down the bottom left there, you see that very blue-looking star, which is Rigel. But if we look up at the top right-hand shoulder, I suppose, of Orion, or left-hand shoulder, where you're looking, you see the reddish star, which is Betelgeuse or Betelgeuse, or whatever, however you want to say it. And this star is a red supergiant. So this is a star at the end of its life. And in fact, if this one here, if we zoom in on it, you can actually take pictures of the surface of Betelgeuse. And that's a pretty amazing idea, because the vast majority of stars we look at on the night sky, doesn't matter how good your telescope, you will always just see a pinprick, a tiny point of light. There's only a few stars which are near enough that we can look at the surface of the object and get details. And Betelgeuse is one of those, partially because it's so large. Betelgeuse is actually a red supergiant, so it would be so big that if you put it where our sun is, it would happily swallow up Jupiter as well. It's a vast star. But it's an exciting thought that we're actually able to look at images and we can see that's a sort of a temperature map to some degree of the surface as well. There's hotter regions, cooler regions on the surface. So we put Betelgeuse in well, so it goes red supergiant in our sequence. So if we come back to our HR diagram to think what's happening now, you have all these objects sitting on the main sequence. They then have swollen up, and because they've swollen up, they effectively move across the diagram. Say the temperature on the outer surface is cooler, a few thousand degrees, rather than some of the objects on the top left. You're talking tens of thousands of degrees, whereas on the right we're talking a few thousand. So the objects move across to that region, but they're really big, and so they're still bright because the cumulative flux from the object is significant, because it's a massive surface emitting a lot of radiation. And so they are in the top right-hand corner of the HR diagram. And what you would see if you could sit and watch a region of stars would be a gradual movement as each star sort of uses up its fuel, it would move across. As I say, the key thing here is that the stars at the top left, so the big stars, use their fuel most quickly. They're greedy, and they get through their fuel faster than the smaller stars. This means of something like some of those massive stars I'm talking about in the Tarantula region, they will only live for a few million years before they expand to become red supergiants. Whereas our sun is there for billions of years, and some of the objects down in the bottom right of the HR diagram will potentially have existed for the entire lifetime of the universe. For 10 billion years they will have sat there on the main sequence, and will sit there for another 10 billion years, because they're using their fuel so efficiently and so slowly that it will take them forever to move to red supergiant phase. So I'd say as time passes, the larger stars would lose their fuel, shift over to the right, and in fact you'd see this sort of change occurring in the graph, and eventually you might see something like this. As all the brighter stars have moved over to be red supergiants. Now, there are other stages, there are other processes. In fact, some large objects will start to do things like they will, because of the way that the processes occur in the core, they might move back across the diagram and go bluish for a while. They might loop round. Some kind of go up. There are other steps involved later on, but they are less common and much shorter. They are far less significant parts of a star's life than these two main bits, main sequence and the red giant branch. Say there are other things, but they're not quite as important. So if we come back to our diagram, we have to think about what happens next. Sorry, so if you go from the red giant, so like our star, our sun will become a red giant. After the red giant phase, the object will, it might move around a little bit, but it will effectively start to fall to pieces. it starts shedding material, and that image I just clicked on is an example of this. This is a planetary nebula, which is the eventual fate for our own sun. It's a very unfortunate name. The name was derived before they knew what they were looking at, but they call it a planetary nebula, even though it's got nothing to do with planets at all. It's the end of the star. Again, fascinatingly, you look at something like that, and it's got those nice spherical structures, which you can kind of picture a star falling to pieces might create spherical structures. Why on earth it creates such asymmetric structures towards the center is anyone's guess. And it's a real challenge to explain that, which is fun. Right at the heart of that planetary nebula is a white dwarf. So that is the eventual fate for our sun. So a white dwarf is something which is about the mass of our sun, maybe a little bit lower because obviously some material has been lost, in an area about the size of the Earth, roughly. So it's very dense, but not ridiculously dense. And it's a fundamentally different kind of beast. It's supported by electron degeneracy pressure, which is a quantum mechanical effect made large, which I'm not even beginning to try and describe because I don't really understand it, but somehow, because of the way energy packs together, the atoms pack together on a quantum level, you can't have them in too small a space, so you end up with something big, which is a terrible description of it, but it's something like that. So that's for smaller objects. Well, something up to maybe 8 times the size of the sun would probably end up as a planetary nebula. And then potentially, if it's larger than that, so something like Betelgeuse, will follow a different route. So they will explode as a supernova. So supernova explosions occur once all that material, you've used up your different things, you've created all your carbon, your oxygen, you've created a lot of iron, and there's no more reactions which can give you energy, in the sense of you could fuse 2 iron atoms together, but that actually doesn't generate energy. It's less, it's lower in, it's higher in mass than just 2 iron atoms on their own, and so it's not an efficient process. So at that point, the star will explode. Again, not brilliantly understood, but effectively the outer layers will collapse in and then bounce back out, and that's it's a extremely quick process, the order of I think a few minutes for the actual core collapse and explosion. What happens to the central regions is they get compressed. So the collapse causes the central regions to get squashed effectively, and will result in either a neutron star, which is something about the mass of the sun in something the size of a city, so that really is very dense, or if the object is sufficiently large, it will actually result in the collapse leading to a formation of a black hole. So if the star is big enough to start with, after the collapse, things become so very dense that a black hole is formed. Just to mention, this one here is the Crab Nebula, which was, again, don't know if it really looks like a crab, maybe a crab shell-ish. This thing exploded about 1,000 years ago, and was recorded by Chinese astronomers because it was so bright that you could see it during the day. And then it was rediscovered in the 18th century, and they found it and they said, well, hang on, they were able to work out this thing was expanding, wind back the clock and say, well, when did it, if you start with something this big and you wind back at the speed it's accelerating, expanding, when did it explode? And we can say it was about 1,000 years ago. So we know that this was that object which those astronomers had seen. This is astronomy in real time, which is a rare thing for us to be able to study. And at the core of this, you've got a neutron star. In fact, you've got a pulsar, which is a particular type of neutron star which emits jets of material along the rotation axis. A little bit like that thing right at the start, but a different kind of jet. So we now have a roughly complete idea of these possible fates. So we either go to a white dwarf or we go to a black hole or a neutron star. So if we go back to our diagram, we should probably just add, for completeness, the white dwarfs, which end up down the bottom. They are very, very dim, but they are very hot. So they fall on the bottom left-hand corner of our Hertzsprung-Russell diagram. So just finally, to talk briefly about the ages of stars. So if we look at a galaxy like this, which is the Andromeda Galaxy, we see bluish and reddish stars, and very loosely and very quickly we can say that bluish stars are probably youngish stars, whereas red ones are likely to be older. They're likely to be either those small ones, which were small ones to start with, and have been around for a long time, or their stars have evolved to be red. If you can see a blue star, it must be fairly young, because otherwise it would have evolved to something redder. So this means that if we look at a patch of stars, if we looked at our HR diagram, so we have our main sequence. If we went back to the same patch and looked at it again and again, as I was doing earlier on with that graph, you would see the HR diagram change shape. So you would see this kink appear in the diagram. And with time, as the larger stars disappeared, the kink would move down the graph. And so this is an example of real data for two different clusters. So the yellow and blue sort of represent different different clusters, and you can see the kink is sort of in different places. Okay, and you can also see that there's obviously a lot more stuff going on here. There's a slightly different shape, but it gives you a feel for what the real data looks like, but also the idea that you can work out the age of a cluster of stars simply by looking where that kink is. If it moves further down, it's older. So if we were to go back to my group of stars, so back to this lovely region here, just give you a feel for a real HR diagram. These are some nice HR diagrams for our massive stars. It almost looks vertical because it's right at the top end of the graph, and actually the main sequence curves around a little bit. And these guys have been doing lots of, this wasn't my work, but these people have been doing lots of studies on trying to work out the different populations within the stars. All the different lines represent different models, etc. And they're able to find out that there are two different formation periods within our region, actually only separated by about 2 million years. But there's an example of the real data which we see. And so finally, if we come back to that original slide I had, so our diagram, we can now look at this patch and we can add in what we know, which is that yellow line I've just drawn in shows our main sequence, and the red line gives us a sort of a red giant branch. But as you can see, this region actually contains stars, lots of stars of different ages. So rather than being one nice cluster, which is nice and neat and has that one bend as the ones I just showed you, this set of data is for a huge region. It's also got white dwarfs in it as well, down at the bottom here. This is data from lots of nearby stars of all different ages and all different types. And so we can actually see that there's still there's the main sequence for all the different stars, but also there's a tendency to see a group along that red line, which suggests there must have been a star formation period, a coherent time when quite a lot of stars were formed, which have now moved across in the diagram, but there are also younger stars in this data set as well. And this is actually data for lots of our nearby stars around the Earth, relatively nearby, obviously I am. And then finally, just to say, so when you go out and see Orion again, look at Orion and you can think about all those different things which we've spoken about. You've got star formation in the sword. You have supergiants, blue supergiants, hot young stars like Rigel down at the bottom there. Then you've got stars which are set to explode any time between tomorrow and the next 100,000 years, which is Betelgeuse up there in the top corner. And I think that's it from me. So any questions? By the way, when it says William Taylor is typing, that's actually Gregor typing because we switched computers. I hope it was useful. I'm never quite sure what level to pitch at. I realise when you're talking to physics teachers, you probably all know an awful lot of this already. So apologies if some of it felt familiar ground. Okay, so black hole formation, again, it's the end when after a supernova, if the star is large enough, then the collapse of material compresses material in the core of the star. So the outer layers are effectively falling in and just, I mean, in the loosest sense, are squeezing everything together. And if you squeeze material enough, you pass into sort of the neutron star phase, which is where you're at the level of the density of a neutron star is basically just the same as the density of the nucleus of an atom. So right in the core of an atom. You can't really get more dense than the core of an atom. So if the star was huge, then when it collapses and compresses the material becomes so dense that it will pass to the level of a black hole. In some ways, a black hole is just very dense material. I mean, just, okay, that's not true at all. It's also a point at which physics breaks down, which is much more interesting. But it's the point at which the gravity has become so tight that the light can't escape it, which is, okay, that just change the physics around it, but in some ways it's just a very, very dense region of space. Does that help, Dharma? I could add that there are also other types of black holes right in the center of galaxies, which are supermassive black holes, and we don't really have a clue how they form, because we have small black holes the size of a star, and we have black holes which are the size of 1 million stars. And we are yet to see anything in between those two, which is a pretty fascinating and bizarre fact. Equally, if you've got any other questions and you want to discuss it more, I'm more than happy to chat offline sometime. Find out who room 2 are.
Not yet.
Still don't know who you are, room 2.
There's a question from Nick forward at the bottom.
It can be tricky with just one star. In some ways you need a few, because, well, okay, that's not entirely true. If you know the brightness and the distance, then you can do quite well. So it's an important point that you really need to know the distance so you can fit it correctly on the graph. So it's harder with one, because you've got to make sure that you know that distance correctly and that you're estimating the brightness correctly as well. We can learn a lot more when we look at a cluster. Yeah, loosely, if you found one and you knew the distance exactly and you knew the the brightness very precisely, then wherever it was on the graph would tell you what it was going to do.
Another question about neutron stars.
Oh, what happens inside neutron stars? Again, they're like the white dwarfs. It's the same quantum mechanical effect. In white dwarfs, it's electrons which are sort of stacked together at different energy levels, so quantum mechanical energy levels. In the neutron star, it's neutrons which are stacked together, which I think is why it's denser. In terms of what happens inside, I think it's a relatively... I'm not entirely sure in the sense of there's no processes like fusion or anything like that. It's the same, this sounds like a cheating way of answering, but it's the same thing as what happens in the nucleus of an atom. And I'm not entirely sure, I have to confess. I don't know how tightly things are even bound. I think things are able to move around, but I don't know whether it's a flow of neutrons or I'm not sure. But it's very, very different physics to what we are used to. Yeah, I should go and read that, actually. Yeah. Good question. Likewise, what happens in the black hole, that's an even more tricky one. Yeah, actually, I suppose really, I don't know whether you should really think of them as particles as well, in the sense of, it's a bit like, say, the nucleus of the atom, we draw it with little blobs, but really that's a very poor approximation, isn't it? In reality. I hope that kind of, okay, it doesn't really answer a question, Jim, but it shows that it's a very difficult question to answer.
Are you happy to share your presentation?
Yeah, fine. Yeah.
Right.
Yeah. No,
Just via that Dropbox link?
yeah. Yeah, that works. I might just switch it for the one I've done.
Right.
Do that. I've got to mention the activity. So for anybody who's still there, I should just say we've been working on an activity which will uses real data, actually from those green, red, and blue pictures I showed. We have an activity where the brightness has been measured, and the activity is for pupils to plot out those points, and then they use model Planck functions which you can print on acetate sheets to try and fit the data and fit a temperature from the data, and then they create their own HR diagram. So that activity is something which we tested out just the end of last week for the first time, and then we're going to put it will be available on the observatory website, but I'm sure Gregor will know how to distribute information about that. Gregor's actually helping us to improve it after our first trial.
Well, I'm not helping you. I'm giving.
Okay, he's giving us money.
Supporting it.
So it'll then be that'll be available. So it will be it's as close to a practical activity as you can I think as you can get in the classroom for HR diagrams.
Alan, I don't know if you can answer that question.
Your mouse.
All right.
Up there. Can I point anywhere in there?
By dragging that around.
Because it's a PDF, I would just, if you move your hand to where you want to be and click.
Right. Okay, yes, apparently there is.
Yeah.
Gordon, you should have asked that question an hour ago. Yeah, that's quite good.
Uncheck.
I see. So if, yeah. Okay.
So you couldn't then click to advance if you were doing that?
Oh, yeah, okay. Yeah. Light wave.
I couldn't not wave my hands around
No, I know.
if I was talking.
Doesn't work.
More feedback coming through.
Did you wake up?
What point did the dog wake up? Hi Celine, I don't know if you can hear me. This is Gregor here. William will be putting it on his website www.roe.ac.uk
Yeah.
/education?
Yeah.
Not sure.
/VC definitely. Oh no, maybe not actually. Yeah, that's it. Sorry, I don't know. Should know that.
Good night, Nick. Celine, if you can email me in a week or two, and I'll send you a link to the diagram. Yes, certainly, Celine, you can do. And I'll pass any inquiries on to William.
Yeah. We're thinking we might put a first version on the website, which has got a few things we know we need to probably change, but we're keen to get something out soon.
So, Celine and Dominique, it was a pleasure having you along. I hope you enjoyed what you saw, and we're hoping that we'll be running these in the future, more of these in the future. The senior courses in Scotland have changed recently, and there's a real need for teachers to tell us there's a real need to be able to access professional learning about it. Thank you very much for signing in. Yes, please do keep in touch with us. We're going to shut the system down now, and as I say, please do keep in touch with SSERC.
Right.